teaspoon of the sun's core is 27 million degrees Fahrenheit, and it weighs about as much as a bowling ball. Now imagine it appears on the table in front of you. You don't get to react. You don't get to run. The air itself catches fire, and the building is gone. But the explosion isn't the interesting part. The interesting part is what that teaspoon tells us about the sun. And it's the opposite of what you'd expect, because here's what we're going to find out. That teaspoon is one of the most destructive objects imaginable. And yet, the sun's core is one of the laziest engines in the universe. Weaker, pound for pound, than the heat coming off your own body right now. Both of those things are true. By the end of this, you'll understand why. And you'll never look at the sun the same way again. Let's start with what's actually in the spoon. The sun isn't burning. There's no fire, no flame, nothing on fire in the way you'd recognize. Burning is a chemical reaction. It needs oxygen. There's no oxygen in the sun, and nothing there to burn. At the core, it's about 15 million degrees Celsius. That's 27 million Fahrenheit. At that temperature, atoms can't hold themselves together. Electrons get torn away from their nuclei, and everything comes apart. What's left is plasma, a soup of naked atomic nuclei moving at hundreds of kilometers per second. Not a gas, not a liquid. A fourth state of matter that makes up most of the visible universe, and almost none of your daily life. And it's crushed. The weight of the entire sun pressing inward squeezes the core to about 150 times the density of water. So your teaspoon isn't 5 grams of anything. 5 milliliters of that is 750 grams. The densest, hottest matter in the solar system, sitting in a spoon. And the moment it arrives on your table, it stops being held together by anything at all. In the sun, that plasma is trapped. Gravity from every direction, holding it in place. On your kitchen table, there's nothing holding it. No pressure, no containment, just air. So it expands, violently, instantly. In under a millisecond, the plasma slams outward into the room, dumping its heat into everything it touches. The air doesn't warm up. It ionizes. The table doesn't burn. It vaporizes. There's no smoke, because smoke requires things to survive long enough to smolder. A blinding sphere of light expands where your kitchen used to be. And this is the part that surprises people. It's smaller than you think. We're conditioned to hear "piece of the sun" and imagine the planet cracking open. It doesn't. Here's the thing we always get wrong. Temperature and energy are not the same thing. A sparkler burns at over 1,000 degrees, and you can hold it in your hand. A bath at 40 degrees will scald you if you sit in it. The sparkler is 25 times hotter. The bath has vastly more energy. Your teaspoon is unimaginably hot, but it's still a teaspoon. It's enough to destroy the building and everything around it. Enough that being anywhere nearby is not survivable. But it isn't a city. It isn't a country. The sun didn't hand you a bomb. It handed you a very small amount of very hot stuff, and hot stuff runs out. Which raises the obvious question. If a spoonful of it is this violent, how is the whole sun not tearing the solar system apart? The answer is the strangest fact in this entire video. The sun's core is barely doing anything at all. Here's how we measure an engine. Not by how hot it is, but by how much power it makes for its size. The sun's core produces about 276 watts per cubic meter. That number is so small it sounds like a mistake. A compost heap makes more. A pile of rotting leaves in your garden generates more power per cubic meter than the core of a star. And you do too. Your body puts out around 100 watts, packed into far less space. Cubic meter for cubic meter, you are several times more powerful than the heart of the sun. Pound for pound, you beat it by a factor of hundreds. You are a better engine than the sun. So why is it hot at all? Because of the only advantage it has. And it's the one thing you'll never compete with. Size. The core is a nuclear furnace roughly the size of 150,000 Earths. Take a pathetic little 276 watts per cubic meter and multiply it by that, and you get 400 trillion watts. Enough to light a solar system for 10 billion years. The sun isn't powerful. The sun is enormous. There's a difference, and almost nobody knows it. But what is it actually doing with all that space? Because the answer sounds like the opposite of lazy. Fusion. Four hydrogen nuclei, squeezed together hard enough, become one helium nucleus. But here's the strange part. That helium weighs less than the four hydrogens did, about 0.7% less. That missing mass doesn't go anywhere. It becomes energy. That's what Einstein's equation is actually for. It's a conversion rate between stuff and light. And the sun does this at a scale that breaks your brain. Every second it converts about 4 million tons of itself into pure light. 4 million tons per second. It's been doing that for 4.5 billion years, and it's barely halfway through. Which sounds like the opposite of lazy. So how can both things be true? Because 4 million tons a second spread across something the size of 150,000 Earths is nothing. It's a rounding error per cubic meter. The sun isn't intense, it's just vast. And the reason it's so gentle is the reason you're alive. Fusion means slamming two protons together, but protons are positively charged, and positive charges repel violently, even at 15 million degrees, even crushed to 150 times the density of water. Two protons colliding in the sun's core almost never fuse. They bounce, trillions of times over. The only reason it ever works is quantum tunneling, a loophole in physics where a particle occasionally appears on the other side of a barrier it should never have crossed. It's rare, absurdly rare. How rare? A single proton in the sun's core waits, on average, about 9 billion years before it fuses. 9 billion years, sitting in the hottest place in the solar system. And even when it finally happens, the sun isn't finished being slow. When two protons finally fuse, they release a photon, a packet of light, and that photon has to get out. But the core is so dense that it travels about a millimeter before it slams into something. It gets absorbed and spat back out in a random direction. Then it hits something else, and again, and again. It isn't a journey. It's a drunk stumbling through a crowd, going nowhere, in every direction for an unimaginably long time. That photon takes roughly 100,000 years to claw its way from the core to the surface. 100,000 years. To cross a distance that light could cover in about 2 seconds, if anything ever got out of its way. And then, the instant it's free, it crosses 93 million miles of empty space in 8 minutes. And that is why you exist. If fusion were easy, the sun would have detonated itself in an afternoon. If the core were as efficient as your body, it would have burned through its hydrogen and died long before Earth cooled. There'd have been no time for oceans, no time for evolution, no time for you. The sun isn't a bomb. It's the slowest, most patient fire in the universe, and its laziness is the only reason there was ever enough time for anyone to look up at it. So, go outside tomorrow. Feel the sunlight on your face. That light started in the core about 100,000 years ago, before your species existed. It has been fighting its way out ever since, and it arrived today. For you. A teaspoon of it would kill you instantly. The whole thing keeps you alive.